Okay, so last time we were talking about deriving, uh, the value, value of E from the time-dependent Schrodinger equation. So, and before my pen went out, so I just I'm going to go ahead and do that and show you that this the time-dependent Schrodinger equation part is actually, yeah, show you how it equals the energy state of the system. Okay, so what I was about to do last time is rewrite the equation. Hope my pen works now. Okay, good. So we have IH bar del psi del T equals E psi. This equation here is a first order differential equation because it's the first derivative. It's the second order del squared, del T squared. And we've seen that in terms of the mass on the spring system where we have md squared x, dt squared equals uh, kx. And so we, made a substitution and we got our solution for a position as a function of time, then took a derivative and velocity and acceleration. But in this case, we're doing it, I'm going to show that this is actually equal to energy. It's a very similar result here because this over here, the time dependent or the integration of of momentum is going to give us the energy. So there's just a number of ways to show that this is actually equal to E. Okay. First thing we're going to do in the ordinary differential equation is that we're going to combine like terms. So we're going to have IH bar, so del psi over psi, that's equal to E del T. Now this del situation is a partial derivative, but we don't have to worry about the vagaries of the partial derivative. We can just go ahead and treat it like it's an actual derivative because we're one reason is it's not part of like a derivative of multiple values at the same time. We're not seeing that one variable is changing simultaneously with other variables. So for the sake of argument, we're just going to look at it as a regular derivative. But in actuality, both variables are changing with respect to each other. It's like, well, one variable sees the other guy changing, and then, well, that same variable sees the other guy changing. So for example, del psi will see del t changing, and del t will say, no, you're changing. So the partial differentiation is like two or more quantities simultaneously changing, whereas a regular derivative is just one value that you know is going to be changing with respect to another. So it's slightly different that way. Okay, so when we have this situation, as we've seen before, we have a IH bar and the derivative of del psi over psi equals E, derivative of del T. And so we're usually going to take this from time is equal to 0 to T. And the wave function, in terms of the boundary conditions, we know that the wave does not exist at 0. So we're just going to say that this is 0 down here, and we're going to go up to psi of T, or whatever you want to say, because this is going to be an integration with respect to time. Okay, so we'll go ahead and perform that integral. So let's see, we're going to have so IH bar, and so we know that the derivative of, or the integral of del psi over psi in this form is going to be natural log. So basically natural log of psi of T. don't have to worry about natural log of 0. It's nothing. Get to that point. So yeah. So the lower bound is not important. And that's going to be equal to E of times T. So we want, so like I said in the previous video, we want to get an expression for the wave function psi, which is a superposition of all of its states. So let's go ahead and divide both sides by IH bar. And then, still not done, of course, divide both sides by natural log. And 1 over natural log is an exponential. And then, since we have this I component here, basically ET over IH bar, we can represent that in a more succinct way. So 1 over natural log is just E, and this 1 over I can be expressed as E to the negative I ET over H bar. So this is the wave function that exists in the time-dependent Schrodinger equation. So H psi is equal to IH bar del psi over del T. So we just solved for the eigenfunction, the wave function for the equation that you see on the homepage of the APC webpage. All right, so now what we're going to do is I'm going to take that result and show that IH bar del psi over del T equals to E psi. All the same stuff. So what we want to do on the left-hand side is make our substitution for psi. So it's IH bar E to the negative I ET over H bar. So now we want to take the derivative with respect to time. And so what we do in this case is we say IH bar. I'm going to take everything out except for time. So when we take the derivative of an exponential function, it's basically without the semantics of chain rule and all that stuff. But in this case, we just take everything out of the exponential and leave time in the exponential. One way we can do this, it's going to be pretty easy, is that we know, okay, from first principles, that I showed you before, that the energy of a wave is equal to HF. We also know that the angular frequency, omega, is equal to 2 pi f. Right? So that basically transforms the first equation here, E equals HF, into E equals H bar omega. So E equals H bar omega is the same as HF. And how that works is, we know that, if you recall from the last video, but I'll write it up, that H bar is equal to H over 2 pi. And since H bar is H over 2 pi and omega is equal to 2 pi f, we see that E is equal to H bar omega, which is equal to HF. Okay? Same thing. I did that to show you that you can, in taking this derivative, you don't have to write out the IE over H bar. You already know from this equation here that E over H bar is equal to omega. So what you're going to basically have is negative I omega times E to the minus E T over H bar. Okay. So that's going to become negative H bar omega, because negative I squared, you know, I is equal to the square root of -1. If you square that, it's just going to be -1. And then negative of that is going to give you positive. So it's just basically say H bar omega. We already know H bar omega is equal to E. So H bar omega, E to the IE T over H bar. We know that this is psi, therefore, we've proven it. IH bar del psi del T is equal to E psi, which is also equal to the Hamiltonian H hat psi. So at the end of the day, we've proven our cause H hat psi equals IH bar del psi del T is equal to E psi. These are all energies, time dependent Schrodinger equation right here, and also time dependent Schrodinger equation right there. But it all equals energy. Energy as a result of the superposition of these wave functions. So in this case, the wave function is going to be I of t equals e to the I t over h bar. We already said that this is a collection of different energy states. So this can be psi of t is equal to psi 1 plus 2 plus however many you got. So this wave function here can be n number of little waves. So in actuality, we're just going to represent this psi of t as a group of small waves that, and we only know how many waves that there are by the n factor in the equation. So ni et over h bar squared, where n equals 1, 2, 3, so forth. So that tells you that this psi of t wave function is a superposition of many states. E to the 1 IET over h bar squared is going to give me a particular waveform. E to the 2 and so forth. So we're in the first wave, we're going to have just a one hump, and then the second one we're going to have 2 and 3 and all the way up for our however many integer values that we have for that wave function. So again, so I just want to do that little addendum. I was almost at the end in the last video to show you, or just to derive the equation at the top of the APC webpage. So tomorrow, I'll be getting into talking about angular momentum, the angular momentum operator, and talking about its particular eigenfunctions. And we'll go into deriving one component of angular momentum. So I'll set up that derivation for you, and then one of your projects that you can do for your quote unquote final is to show that one of the components of angular momentum is equal to a particular form. I'll set up the algebra for you, and then what you have to do is just do a bunch of tedious substitutions and cancellations in order to get to that last form. It's a pretty cool result, but that's about it on this. So let's see if I missed anything. No, it got a little messy there. So I'm not too far into this guy. I think what I'll do, I'll just derive it again. All right. I mean, if you follow that, you can go back over the video. I mean, so IH bar del psi over del T equals E psi. It's the time dependent energy. Energy is a function of time, energy is a function of position. So this is position or time independent, and this is time dependent. So in the first order differential equation, we group the terms just like we did in the second order. The IH bar equals E T. Now we can integrate the terms collected. That's going to be del psi over psi, del T, 0 to T, and the boundaries of the box, 0 to psi of T. Yeah, because I always get that. Yeah, the natural log of 0, undefined. It's not physical, right? So, because yeah, so I remember that. We get closer and closer to 0. It's tending towards 0. So yeah, okay, yeah. Natural log of 0 is just really nothing. So all right, IH bar, natural log psi of T minus natural log of 0, which is just nothing. Definitely anything important. Okay, so this is 0. So ET. That becomes natural log psi of T. IH bar. Okay. Pulling all down to the psi of T guy there. ET over IH bar. By both sides by natural log. One over natural log is the exponential function. So, and then we flip this guy up, it becomes a minus sign. So, you know, it's a little property of the I, but IET over H bar. And I mentioned from first principles HF, this is the Planck formula. We also know that numbers, all that. Okay, so what? Omega equals 2 pi f. And so f will be omega over 2 pi. And so another way of, you know, deriving the same thing with h bar omega. So E equals h over 2 pi f. And no, 2 pi over, sorry. Because f is equal to omega over 2 pi. So it's h, that's going to be omega here. So omega over 2 pi, like that. So, and we also know that h over 2 pi is equal to h bar, and that's how we get the equivalent stance there. So this e over h bar is really just omega. We can write it like e to the minus I omega t, which is the typical form of writing this expression, and that comes out to be sine omega t. I get those get those backwards, sine or cosine. That means sine omega t, which is equal to e to the minus I omega t. And that totally conforms to the solution of the wave function. There's only one, the only part of the wave function that works where the wave function dies out at 0 is the sine function. And we're left with psi of t, e to the et over h bar, which is or sine omega t. Have it. Similar result there, and then you know, whatever, you know, amplitude we can normalize this wave function if we wanted to, and set it equal to 1. When we normalize something, it's going to be equal to all of the values, because mathematically when we normalize something, so we're going to have whatever is here, the x. That basically mathematically what that says in normalizing this, that this is going to be the collection of all possibles. So it's going to be equal to unity, which we call 1. And so once we do this derivation, and especially if we have, you know, it's like in this case, we have a naught sine omega t squared dt, that's equals 1. From this integral, we can get the value of the amplitude, attach that back to the original function, and then we have like a full, a full form of this wave function here. And again, the wave function is made up of little bitty, you know, other wave functions to make up the full wave function here. So that's that on that. Come back tomorrow with the angular momentum operator. Hope you find that one pretty cool as well. Yeah, I just wanted to give you an intro, go through all these little steps to get to the point where we derive that equation, know what it comes from. Now you can understand that that's just an energy equation. It's not conservation of energy, it's just the total amount of energy in a quantum mechanical, time-dependent quantum mechanical system. Again, left with Schrodinger's equation, IH bar, L psi over del t. And I'll write it out in its explicit form. H bar squared over 2m L squared psi plus v psi equals I h bar del psi over del t. Time dependent Schrodinger equation, aka quantum mechanical energy as a function of time. Why do we do time? Remember, a wave can exist in space and time. That's why there are two solutions. So at the end of the day, y of x, psi of x of t is equal to, you know, e to the, let's see, I k r minus omega t. This is the full wave function in terms of space and time. So we can get each of those separate. We can get this guy from h psi equals e psi, which is the time independent solution, which will give us this guy. And then we just got the one for time dependent. Together, this is what works in actuality, because we're saying not only does a wave move through space, but it moves through time. And that's something that we know. It just propagates through space and time, and it has, form, sinusoidal form. This is T, and this is amplitude. Of course, this would be like a mass on a spring, but an electromagnetic wave, for example, moves this way, but it traverses through space and time simultaneously. We can get a full appreciation of a wave traveling through space and time by looking at electromagnetic theory, especially with Maxwell's equations. Also in the physics of antennas, because we're, that's basically sending out an electromagnetic pulse through space and time in order to get to a receiver. So again, all this stuff kind of goes back on each other. Look at a wave moving through space and time from an antenna. We can appreciate it on the quantum mechanical level. And we just arrived that a wave is a function of space and time. So it just keeps on, these solutions just keep on saying the same thing. We can take the same solution and put it in any context: quantum mechanics, classical mechanics. It gives you it really gives you a very good appreciation for why a wave generates from, say, a radio station, to the radio in your car. Based on these first principles, that a wave is a function of position and time. All right, so I've said enough on that. So tomorrow or next time, we'll be talking about the angular momentum operator in spherical coordinates, and a nice little project to follow. Okay. Hope you got some insight in that, and it's been a blast. Okay. Talk to you later.